Hey guys, this is Carrie, and this is the answer key video to Unit 11, Lesson 5. It's not really an answer key, I guess it's a lesson. But take a look at the do now, and come back when you're ready. Let C be a circle with radius r equals 85, and the center of the circle is the origin. Wow, it's so hard to draw circles on here. The radius is 85. Okay, cool. The terminal side of theta intersects circle C at point P in quadrant 2. So in quadrant 2, there's a point P, and we know that we have an angle theta, and it intersects it there. So here we go. There is theta. The y-coordinate of point P is 77. And the r value we know, because it's on the circle, we know the r value is 85. So the one thing we don't know is the x value. And they're asking us to find cosine of theta. So because this angle is so large, we have to not use SOHCAHTOA. We've got to use our updated trig formulas. So we've got to do sine is y over r, cosine is x over r, and tangent is y over x. And so using these updated trig equations, we know that cosine is x over r. And since we want cosine, we need to find x. So to find x, even though it's not apparent, what we've got here is we've got a radius out to a point, we've got a y-coordinate going up 77, and then we've got an x-coordinate here, which is how far back we go. So because we've got a little mini right triangle here, even though theta isn't part of it, we can use the Pythagorean theorem. So we'll do a squared plus b squared equals c squared. A squared is 77 squared. B squared is x this time, and c is always the hypotenuse, so we'll have 85 squared. These ones are a little bit tricky. I don't know if I have them memorized. I think we're going to get 539 here, but let's just do them. 77 squared. Oop, whoa, that's a big number. That's a big number too. All right, let's get rid of all the old calculations. 77 squared. 5,929. Totally wrong, what I said before. So 5,929 plus x squared is equal to 85 squared. So 7,225. Solving for x, we subtract 5,929 from both sides. And we get x squared is equal to 7,225 minus 5,929. So 1,296. And I think we're going to get a nice answer for x. This seems like a square that I know, but I don't remember what it is. 1,296, 36 squared. Cool. So we get x is equal to 36. And now if you put 36 here, that's the best wrong answer, because what we have to keep in mind is the x-coordinate is going backwards. So this has to be a negative 36. All right, so now cosine of theta is equal to negative 36 divided by the arc value, which is r is 85. So we've got cosine of theta. Cool. All right, now to check this out, we find that cosine is a negative number here. Let's see if that agrees with our all students take calculus sines thing. So all students take calculus. The s here means that only sine should be positive. And we found that cosine was overall a negative divided by positive. This was a negative number, so that agrees with our mnemonic. Let theta be an angle whose terminal side is in the fourth quadrant. Okay, so we'll draw a picture. Starting side here, terminal side here. Here's theta. If sine of theta is this, well, we'll use our new formulas. Cosine is x over r, tangent is y over x. So we have y and r from here. Then we know that the y value is 15. We don't know the x value because sine doesn't involve the x value, and we know the r value is 17. But because this whole thing is negative, either the y was negative or the r was negative. R is always positive. It's a distance to the point. And also, if you look at this picture, it looks like we're going some amount in the x direction and then some amount down. Because we're going down, y has to be negative 15. So same as last time, we actually have a hidden triangle here. We've got an x-coordinate, a y-coordinate, which is down 15, so this length is 15, and this r value is 17. So you're going to use the Pythagorean theorem to find x. So a squared plus b squared equals c squared. A is going to be x, b is going to be 15, c is going to be 17. So you get x squared plus, that's not a squared, x squared plus 225 equals 289. X squared is equal to 64. Taking the square root of both sides, x is equal to 8. So we have 8 here. So x is 8. All right, so now we can just write down the cosine of theta. Cosine of theta is supposed to be, according to our formulas, x over r. It's going to be 8 over 17. And tangent of theta is supposed to be y over x. So we do y over x and we get negative 15 over 8. All right, let's check the signs out to make sure that we got them right. So keeping track of our mnemonic, all students take calculus. It looks like only cosine should be positive here. We found that cosine was positive, so that looks really good. We found that tangent is negative. That also agrees, only cosine is supposed to be positive. And sine was negative overall, and that agrees, only cosine should be positive. So everything checks out with our mnemonic. We've got some correct answers. All right, let's put that mnemonic to the test here. So an angle theta is drawn in standard position. It is given these things. So sine of theta is less than 0. What types of numbers are less than 0? Those are negative numbers. Cosine of theta is a positive number. Tangent of theta is less than 0. That's negative. So if we think about our mnemonic, all students take calculus. We want cosine to be positive. That means we're in the fourth quadrant. So they put quadrant 4 because only cosine is positive. All right, let's continue on. So the final piece to be able to find the sine, cosine, and tangent of many angles is this idea of a reference angle. So we're going to take a look at this problem, and you want to lay your diagrams out, 3 diagrams side by side. And we're going to look at 3 similar angles. And we're going to try to figure out something useful from this picture. So from here, sine of theta, well, we know sine of theta is equal to s is y over r, cosine is x over r, tangent is y over x. So actually, you should pause right now and see if you can write down sine of theta, cosine of theta, and tangent of theta without watching along. Okay, so if you pause for a second, hopefully you realized you need the r value. So you do the Pythagorean theorem, and I don't want to go through doing the Pythagorean theorem again. You just do a squared plus b squared equals c squared, and you end up finding that r is equal to 13. So you can check that if you don't believe me by doing the Pythagorean theorem. So writing these down, we get sine is y over r. Cosine is x over r. And tangent is y over x. Cool. All right, so now let's introduce 2 new angles. So alpha is going to be a tiny angle, and it's going to be between, let's read this. It says, in the second diagram, draw an angle alpha. To draw angle alpha, draw an acute angle, so we know it's tiny, between the terminal side shown, so terminal side, and the closer part of the x-axis. So we're going to go to the x-axis, and it's the closer part here. This will be alpha. Okay. So because alpha is not in standard position, it doesn't start on the positive x-axis, we can't use our coordinate plane formulas. None of these work, so we have to cross those out. But we're lucky. Because alpha is an acute angle, alpha can be drawn as part of a right triangle. So let's draw alpha as part of a right triangle here. Alpha is completely inside of the right triangle. And so we can actually use the old trig formulas, so, ka, toa, to find these values. Now the important thing to keep in mind is once these are sides of a triangle, these are all positive numbers because the sides are positive lengths. So the length of this x-coordinate is 12 because we went back 12. The length of this y-coordinate is 5 down, so it's 5 total. And then r, just like we found before, is 13. And we're not thinking about these as coordinates, we're thinking about these as lengths, so they are positive. All right, let's see. Well, sine of alpha, we'll do opposite over hypotenuse. So 5 is the opposite. Oop, that's not the hypotenuse. 5 over 13. Cosine of alpha, that's going to be adjacent to the angle. And we have alpha as our focus angle there. That would be 12 over 13. And tangent of alpha is 5 over 12. All right, let's look at the final example here. In the third diagram, draw angle beta. Draw an acute angle between the terminal side shown and the closer part of the y-axis. So you've got the terminal side. It's going to be an acute angle, so we're not going to go up there because that wouldn't be acute. That's too big. It's bigger than 90. We'll draw beta. Whoa, we'll draw beta here. Great. All right, so here's beta. And because beta is an acute angle, beta can be drawn as part of a right triangle. And we just sketched that right triangle in. And I wanted beta to be inside of it. That's why I drew that triangle the way I did. But you'll notice similar to alpha, because beta is not in standard position, it doesn't start here and then open out, we can't use our coordinate plane formulas that have been so trustworthy throughout the last couple lessons. We actually have to use our old formulas because beta is part of a right triangle. So, ka, toa. Okay, so let's see. Well, because now we're thinking about this as a triangle, all of these are going to be side lengths. So here, this side length here, that's how far we go in the x direction. This is 12 units. This is how far down we go, 5 units. And this is 13 units because we found that to be the case before. And so here we go. With beta, it looks similar to alpha, but let's see what happens. Sine of beta is going to be opposite over hypotenuse, so 12 over 13. Cosine of beta is going to be adjacent over hypotenuse, so 5 over 13. And tangent of theta is going to be opposite over adjacent, so 12 over 5. All right, so we've got our 3 diagrams, and now we need to make a conclusion. So angle theta is the most important angle. We want to be able to find the sine, cosine, and tangent of these big angles in the coordinate plane. And we looked at 2 small angles, alpha and beta. And one of these actually turns out to have really similar answers to theta. If you look at alpha, alpha has the exact same numbers as theta. 5 over 13, negative 5 over 13. 12 over 13, negative 12 over 13. 5 over 12, 5 over 12. It seems like the only difference between these two is that alpha is always positive, and this is sometimes positive or negative, but they have the same numerical values. If you look at beta instead, and you try to match them up, 12 over 13 doesn't really match with 5 over 13. 5 over 13 here doesn't really match with 12 over 13. 12 over 5 doesn't really match with 5 over 12. So it turns out that beta is actually totally useless. Beta is trash. So we're going to cross beta out. We're never going to use beta. We're actually always going to use alpha for the rest of the lesson. And the key thing to remember is, let's see, okay, let's write it down here. Alpha actually has a name. So let's try to write this out in a nice way. Alpha is the positive acute angle between the terminal side of an angle theta and the x-axis. So that was the most important thing about alpha, is that it's between the terminal side and the x-axis. Beta was with the y-axis, if you remember here, and that turned out to be totally useless. It was the x-axis one that was useful. And alpha is called the reference angle. For theta. And the reason why is it's kind of like a reference. It has a lot of the similar values, and we're about to find out just like kind of how much better alpha is than anything we've done before. All right, so reference angle is a key vocabulary word. All right, so let's look ahead. Our big realization, we kind of already wrote it down on the last page. I was looking for where to put that. But maybe we can just follow this up with one more bullet point. Alpha and theta have the same numerical values for sine, cosine, and tangent. And that's super useful. The only thing is alpha is always positive, and theta can have negative or positive values. And we saw that here, like here was negative versus positive. So let's see how we apply these three big ideas. And if I'm moving too fast, feel free to pause, feel free to rewind. This was a big realization here that alpha was useful. So take another look at that if you feel like you would benefit from it. All right, so looking ahead here, determine the sine of 210 degrees without using your calculator. This is actually the problem that if you go back to lesson 3, this actually started us off on this whole process. We found in lesson 3 that the sine of 210 degrees was negative 0.5 using our calculator. But now we actually know enough to figure this out without using our calculator. So let's try to do that. If we graph a 210 degree angle, your first step is always going to be to graph it. You're going to graph it in standard position. So here we go. Theta, well, it's bigger than 90, it's bigger than 180, it's smaller than 270, and so we have 210 degrees right here. We want the sine of 210 degrees, so the first thing that we can think about is, well, is it going to be a positive or negative number? Well, all students take calculus. Because we're in the third quadrant, we know that only tangent will be positive. So we can immediately write down that the sine of 210 degrees is a negative number. Now if we want to figure out what number goes here, or what fraction goes here, then what we can do is we can draw our reference angle instead. Now let's take notes. Our reference angle is alpha. Alpha is always the positive acute angle between the terminal side of an angle theta and the x-axis. So we're looking for the acute angle between the terminal side and the x-axis. It looks like alpha is going to be right here. And if you want, you can actually calculate how much alpha is. Because this was 180 degrees and this is 210 degrees, that little piece in between has got to be, well, this is 180. How much extra do we need to get to 210? We'll do 180 degrees, we'll do 210 degrees, and we'll subtract off that 180 degrees, and that will leave us just with this little alpha piece, which is 30 degrees. So we have this remarkable thing, which is alpha and theta had the same numerical values, just sometimes one was negative and the other was positive. So it must be that sine 210 degrees has the same numerical values as sine of alpha, and alpha was 30 degrees. However, we know that sine 210 will be negative because of the t here being the only positive. So then the last thing here is sine of 30 degrees. Hopefully that rings a bell. That's from your 30, 60, 90 reference triangle. So you sketch that in here. 30, 60, 90, 1, 2, square root of 3. And we know that the sine of 30 degrees is going to be 1 over 2 using opposite over hypotenuse. So we find that the sine of 210 degrees is negative 1 over 2. Wow. So knowing the sine of 30 degrees was super useful because that showed us what the sine of 210 degrees was. Let's do one more of these. Determine the tangent of 300 degrees with how... Oh wait, hold up. Before we go on, we saw this on our calculator, and now we see exactly where that comes from. Oh my gosh. Negative 0.5 is the same thing as negative 1/2. Okay, continuing on to problem 2. Determine the tangent of 300 degrees without using your calculator. So 300 degrees, well, this is 0, this is 90, this is 180, this is 270. If we completed a full circle, that'd be 360. So it looks like we're going to be a little short of a full circle. So here is our 300 degree angle. And we want the tangent of 300 degrees. Now we know that we can always construct a reference angle alpha. And alpha will always be between the terminal side and the x-axis. So here it's not that we had an extra piece. Here it looks like alpha is a missing piece. And if we had alpha in addition to theta, that would have made for us a full circle. So alpha has to be the leftover piece from our full circle. So it looks like alpha is 360 degrees minus 300, and that would leave us with the alpha piece. So you'll notice that there isn't a formula for alpha that always works. Sometimes you're going to be subtracting 180, sometimes you're going to be subtracting 360 stuff. You just have to do it based on the picture. Here alpha is 60 degrees. So we know the tangent of theta is always going to be the same numerical value as the tangent of the reference angle, which would be tangent of 60 degrees. The one thing to keep in mind, though, before we find that is, if we write our letters, all students take calculus, we know that only cosine will be positive here. So we must write that this is negative tangent of 60. So tangent of 300 degrees is equal to negative. And then to find the tangent of 60, we go back to our reference triangle. We focus in on 60. We do opposite over adjacent. So tangent is opposite over adjacent. And we find that the tangent of 300 degrees is going to be equal to negative square root of 3. And so without using our calculator, we're actually able to figure out the sine, cosine, and tangent of all of these big angles that before would have been impossible. So I think the rest of the lesson is practice. Yep. This one should say 173 degrees. Sorry about that. And the rest of it looks good. So this was a much shorter lesson. Please do the practice problems and send in your checkpoints.